Good afternoon to all. So let us continue our lecture number 5. And by the way, do you have any doubts or comments from the previous lecture so that we can discuss and proceed further? So before starting the uh, thing, so do you have any questions or doubts?
No, sir.
Okay, good. So let me just recall that in the previous lecture, what our aim was to uh, prove the fact that this ring of so polynomial ring with integer coefficients is a unique factorization domain. And in order to do so we have proven the so-called Gauss lemma, and as we have seen that this plays an important role in order to establish the divisibility from q of x to z of x, yeah, like in order to prove these results. And what we have also saw that means if you have a polynomial which is irreducible in z of x, then it will be irreducible in its field of fraction, say q of x, yeah. And then what we have shown using this thing, that using this much information in order to prove UFD, what we know by a theorem, that we need to show the existence of factorization plus every irreducible element should be prime inside that integral domain. And so with this much of work, we can show that well, existence of factorization holds inside z of x. And in order to do so, what the argument can be floated is that if you take a polynomial in z of x, well, you can write this polynomial in terms of primitive polynomial by using a lemma that we have proven here. And this lemma is exactly this one, yeah, very natural to prove this lemma. And so using this, we will write in terms of these primitive polynomials. And since the coefficients are from z, so c, the content will be an integer. And so what you can do, that you can factor this integer in terms of prime integers, that's obvious. And now only thing we have to see whether this primitive polynomial has the existence of factorization in terms of irreducible elements or not, yeah. And so what we do, that we think of this polynomial inside q of x, and q of x has a factorization, and then we will use this information. So we will write the factorization of f0 inside q of x, and then we will use this argument that if we have factorization inside q of x, then we do have a factorization inside z of x, yeah. And then using these arguments, we can show that existence of factorization holds inside z of x. Now the only thing that will remain to prove that every irreducible element is a prime element inside z of x. And then what we have done, that we have first analyzed what are the irreducible elements inside z of x, how they look like. So they may be a prime integer, so irreducible elements may be the prime integers, or if it is a non-trivial polynomial, so it has to be a primitive polynomial, which should be reducible, of course, inside q of x. And primitive is a natural assumption, because if it is not primitive, and so if GCD has some non-trivial integer, then it has a this polynomial can be written in terms of, then this polynomial may be reducible, yeah. So the primitiveness is important in this one. And so this was the characterization that how irreducible polynomials inside z of x looks like. And using this, what we have proven, that if you take any irreducible element inside z of x, is in fact a prime element. And the arguments that we have floated, that if you start with an irreducible element, so irreducible elements inside z of x will be either a prime integer, so we'll consider the case f is a prime, and then we showed that it is in fact a prime inside this z of x also, yeah. And the second one was if it is of the form primitive irreducible inside q of x, then using the fact that this is a PID, and so irreducible element will be a prime inside q of x, and so therefore divisibility happens inside q of x. where f is a primitive, and then we will use the proposition part A of the proposition, which says that if you have primitive polynomial inside z of x, which divides another polynomial with integer coefficient, and if the divisibility happens inside q of x, then in fact this divisibility happens inside z of x also. Yeah. So and so therefore it proves that z of x is a unique factorization domain. And so let me just continue this today's lecture. That so we'll write it as a proposition. And so what we can write it down, that this is proposition, that so z of x is UFD. Yeah, and now I will leave it as an exercise to you to write down the complete detailed proof of this fact. And so this is homework, as we have discussed in the previous lecture. Now what I would like to say, that if you take R to be any unique factorization domain, so R to be a unique factorization domain, so therefore the arguments that we have floated in this previous lecture, like first one can define the notion of so-called primitive polynomials, and there one can so instead of an is positive, one can put the that condition that this leading coefficients should differ only up to units. Yeah, so if one writes up to units definition, and then if one follows the arguments that we have floated in this thing, then one can prove the results that we have, for example, proven here, this proposition. Instead of z, one can replace r, and wherever q is there, one can replace it by its field of fraction. And one, if tries to mimic the arguments, then one can in fact prove that this Rx is in fact a unique factorization domain. Yeah. Then if you look at the polynomial ring, R of x is a UFD. Yeah, UFD. Yeah, and so what using this, what one can in fact say, that if you know that I think you know this fact, R of x1 x2 is isomorphic as a ring as R of x1 x2. Yeah, and since what we have proven that if R is a UFD, then Rx is a UFD, and so therefore this will imply that R of x1 x2 is also a UFD. Yeah, and so in general one can write as a proposition that let R be a UFD, be an UFD. Then if you try to look this polynomial ring in many variables, R of x1 and so on xn is again is a UFD. Yeah, and so in particular, for example, so z of so what we can say, that in particular, so we have this if you look at the polynomial ring in many variables with integer coefficients, so z of say x1 x2 and so on so forth xn is a UFD. Yeah, is a UFD. And similarly, if you have a polynomial, if you have a field f, then what we know that f of x1 is a PID, and so it is a UFD. And using the arguments like this, one can prove that f of x1 and so on xn is a UFD. Yeah, where f is of course a field here we are taking. And so this is about this unique factorization domains, and when one can say that if you take an integral domain which is a UFD, then if you look the polynomial rings over that integral over that UFD is again a UFD. Yeah, so this is all about this thing. So let me just I start giving a particular example by taking this field f to be a field of complex numbers. and then we will proceed further. Yeah, so if we take this f to be c, so what we have that, so if you take f to be c, so we can take c of x, for example, c of say x1, c of x is a principal ideal domain that we know, but what we know that c of xy is not a principal ideal domain, but it is a unique factorization domain, is UFD. Yeah, and now and what we know, for example, if you compare with c of x, so c of x has a very important nice property that of course it is a PID. Yeah, c of x is a PID, and in fact what you know that if you take any polynomial inside c of x, for example f belongs to c of x, it has a very nice property that this the irreducible elements inside c of x are the linear polynomials, that f of x can be written as some constant times say x minus alpha 1 and so on, x minus alpha n. Yeah, but if you go for example c of a polynomial ring in two variable over the field of complex numbers, so the irreducible elements may be degree more than one. Yeah, so this is the thing that I would like to just say, that the irreducible elements, even structure wise they are different, even the irreducible elements also behaves differently. For example, we may get an irreducible element of degree 2 in with polynomial ring in two variable over the field of complex numbers. Yeah, so for example, if we try to look this, for example, if we look at the f of xy to be x square plus y square minus 1. Yeah, so this is a polynomial which lies inside c of xy. It is an element inside c of xy, and as you can see that the total degree of this polynomial, so if you try to see the total degree of f is equal to 2. Yeah, and now we need to check whether it is reducible or irreducible. So well, so one way is that we use that is the conventional, or by definition that we will write it as a product of two non-trivial factors, and we try to do certain analysis and say that such a factorization, and check that whether such a factorization holds, and this will give you the answer. And since we are in a very low degree, degree 2 only, so this method will work perfectly. Yeah, however, sometimes we can use the sort of geometric arguments which also will be giving precise answers in some cases, and this is the particular example. So for example, if you try to look this locus, or what you have been told in terms of algebraic geometry as a variety, so if you define the locus of this polynomial, say all those points x, y, and c, such that f of xy is equal to 0. Yeah, so if you look at the locus, and so inside, if you try to look the locus inside say R2, so inside R2, so this will represent a circle. Yeah, so W will represent a circle, and suppose f is reducible. Yeah, so what we can assume that suppose f is reducible. So first of all, let us try to see over R. So what we can see that over R, so this W represents a circle, and if it is reducible over R, so what we can see that if you write f as product of two say linear factors, so it will have two non-trivial factors which will be degree 1. Yeah, and so if you try to look the locus of, or the variety defined by the polynomial g and h, so for example, if you write u to be g of xy is equal to 0, yeah, and v to be the variety defined by the polynomial h, which is all those points for which h of xy is equal to 0. Yeah. Now if you try to see that the factors, they will be linear. So g of xy will be of the form, for example, so this will be of the form ax plus by plus c. Yeah. So therefore what we see that the variety defined by the polynomials g and h are actually the straight lines inside this real line, lines inside R2. Yeah. And so therefore what we see that we can write this variety w, or this locus w, in terms of union of the locus of g and h. So w is equal to u union v. Yeah. But as you know that this is not possible, because circle cannot be written as union of two lines. Yeah. And so therefore this decomposition cannot happen. So therefore what you can say that such a decomposition cannot hold, and so therefore f is irreducible in Rxy. Yeah. So this implies that f is irreducible in Rxy. Yeah. Because what you can say that this, if such a decomposition exists, that means that the circle contains a straight line, which is not possible. Yeah. F is irreducible in Rxy. So what we have shown that if you take a polynomial in C of xy, we will geometrically very well see that it is of course irreducible in R of xy, but one can use the same or similar arguments to say that actually F is irreducible inside C of xy. Yeah. Because there also, if you try to write it as suppose it is reducible, then one can write f in terms of degree 1 linear polynomials, and then what one can say that all the real points are actually the points, all the real points of w, actually the points of w inside, if we consider it as a variety defined over C. Yeah. In the complex C2 plane, in C2 plane. Yeah. So all the R2 points will actually be points inside C2, and similarly this variety defined by say u and v, like a variety defined by g and h, actually the points corresponding to, so so what I would like to say that this circle, real points of this real circle will lie in this union. Yeah. And since there are more than at least more than 2 points, real points inside this circle, so they will so one of this u and v will contain at least 2 real points. And if you have 2 real points, so you can find equation of line by, if you know the 2 real points, then you can find the equation of line passing those 2 points. And one can say that actually in that case also this locus w contains a line which is real up to a constant factor, and which will contradicts the fact that circle doesn't contains line inside C2. And therefore one can in fact prove that f is and similar arguments. So one can prove that using the similar arguments that f is irreducible in C of xy as well. So therefore what this argument actually says that sometimes it is helpful, sometimes in order to check irreducibility or reducibility of a polynomial. So for example, suppose f is given inside say C of xy, and in order to check geometrically whether a polynomial is reducible or irreducible, what one does that, suppose it is reducible, then one writes it as f g into h. So suppose f reducible. So what one does that one writes f as g into h, and now one defines the locus or the variety defined by these polynomials f, g, and h. So w will be the locus of this polynomial f of xy is equal to 0, and u will be the variety say locus defined by the polynomial g of xy is equal to 0, and v one can define to be the locus defined by the polynomial h of xy is equal to 0. And now if if f is reducible, then this locus w can be written as union of two varieties u union b. And if you know a bit of geometry about these w, u, and v, then one can actually check that by geometry that such a decomposition is not possible. And if so happens to conclude that such a decomposition I mean that this w cannot be written as union of two other varieties, such a decomposition is not possible, then one can say that one can conclude that f is irreducible. Yeah, so this is a bit of a glimpse how this algebraic geometry or the problems of algebra can be dealt by the geometric arguments, or by realizing the geometry behind these geometry behind these polynomials. Yeah. Okay, so far so good. And so this is the thing that I just would like to mention. By the way, one can very simply prove that this polynomial is irreducible by algebraic means. So let me just sketch the proof that how one can prove algebraically. So algebraically, so are there any questions or comments?
No, sir.
Okay, fine. So for example, here algebraically, it is very easy in this case to prove, because the way we used to prove that, we write x square plus y square minus 1 into product of, for example, let's say two linear factors, say ax plus by plus c, and the other factor, suppose a dash x plus b dash y plus c dash. And now what you do, you try to compare the coefficients of both of these sides. And then if you compare the coefficients both of these sides, and then you will get certain contradictions. For example, if you can see that the coefficient of x square will satisfy, I think a dash is 1. Yeah. And if you try to
b dash equal to 1, c dash equal to -1.
yes, for example, c dash is equal to -1, and then b dash is equal to 1. This is one set of relations. And other one, if you try to compute the coefficient of x into y, so
a b dash plus b a dash equal to 0.
yes, yeah. So yeah, and for example, if you try to compute the coefficient of x, so it will for example, it will be like c dash a, yeah, c dash a, this is the plus and so on. So you will get certain relations, and if you try to solve these relations, then you will get contradiction. Yeah, and then it will prove that such a decomposition is not possible, and then you will say that this polynomial is irreducible. Yeah, so you can do this thing by yourself, and I just sketched the how one can proceed. So one need to uh, solve a certain set of equations, and then one will be getting contradictions. For example, here it shows that all of them are non-zero and they satisfy certain equation, and the remaining equation will give you certain contradictions to one of these conditions. Yeah, so in this way one can algebraically prove that this polynomial is irreducible over C of xy. Yeah. So this is the thing. And so now let us try to actually discuss so-called the explicit factorization of polynomials. And so far we have discussed the what are the irreducible, what do we mean by irreducibility inside a unique factorization domain. And there we saw that actually every irreducible element is a prime element, but sometimes in order to check whether a polynomial or an element is reducible or not, we need to actually do explicitly or check explicitly how one can actually confirm that whether a given polynomial, for example with integer coefficient, because over R or C it is not difficult, and the difficulty comes if you look at, for example, field of complex numbers or a ring of integers. And if you look the polynomial over this, so they are more actually describing irreducibility inside Q or Z is much more difficult than R or C. Yeah, so here we are going to discuss certain results which will actually ensure that when one can say a given polynomial is irreducible or reducible. Yeah, and so in the literature this is known as the explicit factorization. Explicit factorization of polynomials. Yeah, so for example, if you take a polynomial f of xy, sorry, f of x, for example, take in one variable first, and then we will discuss maybe in two variable at the end of this topic. So what you can do, you have polynomials, say an x to the power n, and so on, so forth, so on, a0. And suppose this is a polynomial inside with integer coefficients. And so we would like to find the, for example, irreducible factors of this polynomial over z of x. Yeah, so and what here we would like to, first of all we would like to know the irreducible factors of, so actually want what we want, that irreducible factors of fx inside, first of all, q of x. Yeah, but in order to know the irreducible factors of fx inside q of x, what we can deduce a reduction step that enough to know the irreducible factors inside z of x, in z of x. And this is just because in the previous lecture we have proven that if you have a irreducible polynomial in z of x, this corollary, if you have a irreducible polynomial in z of x, then it will be automatically irreducible in q of x as well. So therefore we would like to know, for example, the irreducible factors of this inside z of x. And for example, if one is interested to find the linear factors of this polynomial, and linear factors are easy to handle, just because if there is a linear factor, say b1x plus b naught, and if it divides this f, so what we can see from this thing, that what we can say, that b1 should divide an. Yeah, because if you write f as b1x plus b naught times another polynomial, let's say star, and if you try to compare the x to the power n coefficients, then you will see that the coefficient b1 will be multiple of some other integers, and which will be for example equal to an. And then you can say that b1 divides an, and say b0 divides a0. This is the one way. And now you know that there are only finitely many divisors of an and a0, and one can check case by case analysis to find the linear factor. So this is the one way that one can do. Otherwise, what you do, that you look this polynomial and look, for example, solve this for x is equal to, say, minus b0 by b1, and you plug this value inside this f of x, and say and check whether it is 0. Yeah, then also you can actually analyze the linear factors of this polynomial. But if the polynomial is, for example, higher degrees, then it becomes difficult to analyze the factors of this polynomial. And in order to do so, like so this was in fact it is again still a problem to investigate to find the irreducible factors of such polynomials. And in this direction, Kronecker actually showed a method by using the Lagrange interpolation formula, that how one can find the factorization of a given integer polynomial. But a lot of research or investigations has been done in this direction, and in fact better results are known. And in fact this Lagrange interpolation, as you might have studied in other subjects or even in algebra also at some point, that this the conditions that it requires actually takes a lot of steps to do the process. Yeah. And so let me, what our aim is to discuss or find certain information about integer polynomials by knowing certain information. If you go modulo p, yeah, so computation modulo p actually helps in this direction perfectly at some point, and we are going to discuss certain results in this direction. And one of the famous result about irreducibility of an integer polynomial here that we know, that is the Eisenstein criteria, actually is nothing but the reduction modulo p result, actually, in a sense. Yeah, so and we will see today that this how this Eisenstein criterion that is actually famous to sometimes deduce irreducibility of integer polynomials when they meet certain conditions. Yeah. And actually we will see that though the results is stated in terms of primes, but the proof actually uses the reduction mod p arguments. Yeah. And so today our aim is to discuss this reduction modulo p steps. And so what is actually this reduction modulo p is these arguments actually do. So we have here, so for example, polynomial over integer entries. And so we have a natural homomorphism from z of x to z mod pz of x, polynomial ring over the field z mod pz. And well, what we have, so we have given f, we can just reduce the coefficients modulo p and look t. Suppose you have polynomial with integer coefficients belongs to say z of x. Yeah, so what we can say that if f is reducible, if f is reducible in zx, what does it mean? That what does it mean? That is, f is product of two polynomial with integer coefficient, and this is written non-trivially. So what we see, that this implies that if you reduce modulo p, say f bar is equal to z bar times h bar. Yeah. So what we see, that if a polynomial with integer coefficient is reducible, then it is reducible modulo p for almost all primes. Yeah. So then f is reducible mod p for all primes, say. Yeah. So therefore, if you try to so what does this actually says, if you try to think of contrapositive statement, that if there is some prime p for which f is not reducible, that means f is irreducible, then can we say that the original polynomial with integer coefficient is irreducible? Yeah. And as you can see that this implication actually says that that should be true, because this is exactly the contrapositive statements and they are equivalent. Yes, and that is indeed true with certain conditions that one need to take care while writing this contrapositive statement. And so that is the thing we are going to prove as a proposition. So let me just write down it as a proposition. So what does this say? That so let f of x, if you have polynomial with integer coefficients, say an x to the power n plus say an minus 1 x to the power n minus 1 and so on so forth a naught. So this is an integer polynomial, yeah, and let p prime such that p doesn't divide the leading coefficients an, yeah. Now if f bar, if you look the polynomial reduction modulo this prime p, if f bar belongs to say z mod pz of x is irreducible, then one can say that f is irreducible, then f is irreducible in, so f is irreducible in where it will be irreducible, can you say what should I write here, q or z? So can any one of you say something? Z,
Yes,
zx, for example, but in z, so it is a polynomial, and
oh, qx
if it has certain GCD, and if GCD happens to be not plus minus 1, so that will be, for example, prime, so that will be irreducible factor in Z.
Q.
Yeah. In QX, that is treated as a constants, like they are invertible elements, so that will not be a problem. Yeah. So they will be irreducible inside Q of X. Of course, if you start with a primitive polynomial, then one can say that it will be reducible inside Z of X. Yeah. Yeah, primitive, if you have primitive polynomial which is irreducible in QX, one can prove that is of course irreducible in ZX. Yeah. So this is the bit of catch in this proposition. And so it is, so the proof, I think, you can of course prove by yourself. So one thing that here, so of course, as I told that f I can write, if I would like to write in terms of primitive polynomials, so we can write c times f0, yeah, where f0 belongs to z of x and f0 is primitive. Yeah. So the proof that I would like to give here, that instead of assuming f, we will very well work with f0, because since p doesn't divide the coefficient an of f, and this will actually imply that p as well doesn't divide the coefficient, leading coefficient of f0 as well. Yeah. So what I am, so without loss of generality, what we can assume that f is primitive. And we will work with the primitive polynomial, and then if you work with primitive polynomial and if you prove that is irreducible in qx, well, it will be irreducible in zx also. Yeah. So if f is primitive, and suppose let us the proof is we will natural or the method of contradiction in this type of arguments most of the time works, that if you would like to prove irreducibility, so assume that it is reducible, then that means what, f can be written as g into h. Yeah. And now here, since we are in the case of what here we have, that f is primitive, we have assumed that degree of g and h has to be positive. Yeah. Because they cannot, one of them cannot be degree 0, because degree 0 will corresponds to so let me write precisely so that it will not, suppose f is reducible in q of x. Yeah. So this implies that f is reducible in z of x, reducible in z of x. And this is just because by the previous corollary that we have discussed here, that if f is irreducible in zx will imply that it is irreducible in q of x. So if you write the contrapositive of this statement, which will say that f is reducible in qx implies f is reducible inside z of x. Yeah. So using that, we can write this factorization in z of x. Yeah. And since f is primitive, one of them cannot be like prime integers. Yeah, because primitive, it will not have any non-trivial, it will not have any GCD. It will not have, for example, any content. So therefore, so since f is primitive, implies that both have degree of g and degree of h, both are positive, strictly positive. Yeah. Now, so what we are going to do, we go to the reduction modulo p step. So that will say that f bar is g bar times h bar. Yeah, and note that degree of f is same as degree of f bar, and this is because since this is just because that p doesn't divide the leading coefficients. So therefore, the leading highest degree will be the same if we even go reduction modulo p. So therefore, degree of f is same as degree of f bar, and this will imply that actually that degree of g is actually same as degree of g bar, and degree of h is same as degree of h bar, and both are positive. Yeah, the degree of g and h. So therefore, what we see that this implies that f bar is reducible in z mod pz of x. Yeah, which is a contradiction to the fact that we have assumed that f is irreducible in z mod pzx. Yeah, and so therefore what we have deduced from here that thus we are done. Yeah. So therefore, what we have proven that if we are able to find a single prime p, for example, we can check it for small primes like 2, 3, 5, 7. And if at some point, if we are able to get that the degree of f and degree of f bar are same, and if we go modulo p, then f bar is irreducible in z mod pzx, then in fact we can say that this polynomial is in fact irreducible inside z of x as well. Yeah. So this is a result, but let me just write a remark that this method most of the time though work, but it is not the complete answer. Yeah. So this is just a remark actually, that what I would like to say that there exist. So what I would like to say that there exists. So there exists polynomials fx. For example, if I take the polynomial x to the power 4 plus 1, this is irreducible in q of x, but it is reducible modulo p for every point, but it is reducible mod p for every prime p. So this you can try by yourself, that why this polynomial is reducible modulo every prime p. Maybe in tutorial or at some point, maybe in the next lecture, we can discuss. If you have done, then it's fine. Otherwise, we will discuss maybe in the next lecture that why this polynomial is reducible modulo p for every prime p. Yeah, so therefore, so this method means not perfectly able to check the irreducibility of all polynomials, but of most of the time this method actually works. That's what I would like to say. So this is the one thing. And so what we see that the reduction modulo p step actually gives us certain information about the irreducibility of a polynomial inside z of x, provided if one gets a polynomial, if one gets a prime p for which f bar is irreducible modulo p with degree of f should be equal to degree of f bar. That is the important thing. What I mean to say that if somehow if you see that the degree of f bar is lower than the degree of f, and you can see that the f bar is irreducible, then one cannot conclude that the f is irreducible inside z of x. So the degree of f is same as degree of f bar actually is the condition that this local condition that p doesn't divide an. Yeah. So this is the thing. And well, what I would like to say from this statement, that this statement actually requires the information that if somehow we will get a prime for which f bar is irreducible, then we can say that f is irreducible. But now what we would like to say that actually sometimes actually what happens that even if we are able to know that f bar reducible, sometimes we'll be able to give the information about irreducibility of the polynomial f inside z of x. So for example, so let me just convince this thing by an example. So and then we will proceed further. So for example, if you look at the polynomial, say f of x is equal to say x cube plus 6x plus 3. Well, this is inside say z of x. Yeah. And now what you do that if you reduce modulo p, so f bar, if you try to see f bar of x is x cube, which lies inside z mod say 3z of x. Well, now what we would like to check whether this polynomial is irreducible or reducible. So what we can do that, suppose f is reducible, suppose f reducible. That means what, that f we can write as g times h. Yeah. And let's say it is degree 3. So for example, let's say it has factors of say g, and h for example has factors say ax plus b, one linear factor, and one say degree 2, say cx square plus dx plus e, one degree 2 factor. Yeah. Now if we go reduce, if we go modulo 3, so f bar will be say g bar times h bar. Yeah. And so therefore what we see that g bar should divide f bar and h bar should divide f bar, right? And so if you try to see that if g bar divides f bar, that means that a bar x plus b bar should divide x cube. Yeah. So this implies that so b has to be 0 mod 3. Yeah, because it is a monomial. So the divisibility is in monomial is by a monomial. And similarly, h bar divides f bar means that this e has to be equal to 0 mod 3. So similarly, what we can see, similarly, e has to be 0 mod 3. Yeah. Yeah, but what we see that b into e, if you try to see, should be equal to 3. Yeah, if you try to compare the constant coefficient of this factorization, what we see, but b into e is equal to 3. Yeah, so therefore b into e is equal to 3 means that b and e both are non-zero and their product is 3. But here what we see that both are divisible by 3, which is not possible. Yeah. So which is not possible means we cannot write f into the product of two factors of this kind, though f bar is reducible. Yeah, though we know that f bar is reducible into linear factors. Yeah, x, x, and x. Yeah. So therefore, what we see that using this, so thus no such factorization exists. Thus no such factorization exists, and hence what we can say, and hence f is irreducible. Yeah, and hence fx is irreducible. And so what I would like to say that even if we know that f bar is reducible, actually gives irreducibility of integer polynomial, and the steps that we have sketched in this example are actually the steps of the proof in the Eisenstein criterion that we are going to see. So let me now just write down what do we mean by this Eisenstein criterion, and then we will proceed further. Yeah. So let me just write it as a proposition, and then we will proceed. Yeah. So this is the proposition, and it is known for Eisenstein criterion. So what does this say is that, so you have polynomials, say fx, say a0 plus a1x, and so on so forth. An x to the power n is an integer polynomial. Yeah. And what happens that, so you have a p a prime, yeah, such that the following condition holds, that such that the first one is that p doesn't divide the leading coefficients. This condition is was also in the previous proposition. And the second condition what here we have, that p divides the other coefficients, like in this example we have seen p divide 3 divides these two, and so we will write as p divides, say, an minus 1, and so on, comma a0. P divides all the other coefficients. And the third condition is that p square does not divide a0. Yeah. So if we have these three conditions about the coefficient of a given polynomial with respect to a prime, and if these conditions are met, then this Eisenstein criterion actually says that then f is irreducible in Q of x. Yeah. And so let us and so this is the one of the important result in order to check the irreducibility of a polynomial. And let us try to see the proof is exactly the steps that we have discussed in this example actually. And so let us what we are going to do is that suppose what we are in order to prove this, again method by contradiction we will apply, that suppose f is reducible. Yeah, suppose f is reducible in Q of x. Yeah, then what? So this implies that f is reducible in Z of x by the corollary in previous by this corollary that we have just written down. So f is reducible in Z of x, so inside Z of x. So that means what? That f can be written as, say, g times h. That's true. We can write, and this factorization inside Z of x. So this is inside Z of. Yeah. And now what we do, we go modulo reduction modulo p step that we have done in this case. Here we have gone into modulo 3 here in this example, and similarly here also we will go modulo p. So this will be f bar will be exactly equal to g bar times h bar. Yeah. And if you try to see that f bar will be precisely a monomial, like here it was x cube, and here instead of simply, here it will be a monomial with coefficients a n bar. Yeah, because all the other coefficients are divisible by p. So this will be exactly equal to, say, a n bar x to the power n. Yeah. So what we see that from this, that g bar divides a n bar x to the power n, and h bar also divides a n bar x to the power n. And so therefore what we see that this polynomials actually divides this g bar, and h bar divides the monomial, therefore they has to be monomial. Similar arguments that we have floated here, that b bar has to be 0, which will say that this should be a monomial. Yeah, similar arguments will say that this g bar and h bar should be a monomial. Yeah, should be monomial. And so therefore what does it says that the polynomial g and h, and if you try to look the coefficients of this polynomial g and h, so what we see that all the other coefficients are divisible by p. Yeah, so uh, so so what we see that all other this implies that all other coefficients of g and h except the highest degree are divisible by prime p, are divisible by this prime p. Yeah, and so therefore what we see that now what we see that suppose this g and h has constant coefficients as a naught and b naught. So let me just write down that let the constant coefficient of g and h are a naught and b naught respectively. So what we see that no, for a naught is for, I think I have assumed for f, so we can assume that b naught and c naught. Yeah, so let me just erase this thing. So this would be b naught and c naught, and so, and if you try to combine these two, we will get the coefficient of a constant coefficient of f, which is a naught as b naught c naught. Yeah, so what we see that since this prime p divides b naught and p also divides c naught, just because we have seen that all other coefficient except the highest degree will be divisible by p, so therefore this constant coefficient will be divisible by p. And so therefore what we see that this implies that p square divides a naught b naught, which is exactly equal to sorry, p square divides b naught c naught. Yeah, because it is here c naught, and this is exactly equal to a naught, which is a contradiction, and this is a contradiction to the this fact, the third fact that we have here, that p square should not divide a naught, but we are getting the fact that p square divides a naught. Yeah, and if you see the steps of the proof exactly has been analyzed in this argument, that what we have got that b 3 divides b and 3 divides c. Yeah, therefore 3 square should divide the constant coefficient of f, which is a contradiction here. Yeah, so and therefore what we see that actually the both part of the reduction mod p is helpful to reduce irreducibility of a polynomial with integer coefficient. So if somehow if we get a prime p for which f bar is irreducible and degree of f is same as degree of f bar, then one can say that f is irreducible. If not, if somehow you get some prime p f bar for which f bar is reducible, that we have discussed here, and if along with those conditions, if you get this type of conditions also, then you can as well say that f is irreducible inside q of x. Yeah, and of course here also irreducibility in q of x provided. So if you want irreducibility in z of x, one need to start with a primitive polynomial. Yeah, so this is the thing, and about Eisenstein criterion. So let me quickly give a what I should say application of this Eisenstein criterion, which is about the irreducibility of a cycloatomic polynomial. So let p be a prime, so let p prime. Yeah, and then the polynomial, then if you take the polynomial f of x to be x to the power p minus 1 plus x to the power p minus 2 plus and so on so forth plus x plus 1 is irreducible. This polynomial is irreducible inside q of x. So I think as you can see, it is not a direct application of this Eisenstein criterion, because we will not get any prime p which satisfies the conditions of this polynomial p, this polynomial f with respect to any given prime, because all have coefficients 1 and no prime divides 1. Yeah. And so here is a trick that actually gives the proof of this thing. So what one does that we need to, so this trick actually helps to prove this application by using Eisenstein criterion. We will look x minus 1 times fx. This thing will give me the identity x to the power p minus 1 that one can check. And now what we are going to do, we will just change the variable x by p y plus 1. For example, if you replace x by y plus 1, so what we will get, that y times f of y plus 1, if you try to see, that we will get that y plus 1 to the power p minus 1. Yeah. And if you try to simplify this, so what we will get, that y to the power p plus p choose 1, then we will get y to the power p minus 1 plus p choose 2, then we will get y to the power p minus 2, and so on so forth. We'll get that plus, say, p choose p minus 1, then we'll get y. Yeah. And now what we can do is the following, that as you now here one can apply this Eisenstein criterion, and in order to apply, so let us first divide by y. So what we will get, that f of y plus 1 will be exactly equal to y to the power, say, p minus 1 plus p choose 1, then y to the power p minus 2, and so on so forth, plus p choose p minus 1. Now here it is very visible that one can apply the Eisenstein criterion, and then so apply Eisenstein criterion here. And well, in order to apply the Eisenstein criterion, one need to make sure that this prime p divides p choose I if I is strictly less than p, and that happens for prime. And this is one of the important property of prime that we are using here, that since p divides p choose I, where I is strictly less than p, and this is one of the important property that is only true for primes. This property is not true for composite integers, and that's the crucial fact we are using, that we are in the case of prime p, apply Eisenstein criterion for f of y plus 1 and prime p. Then we will see that then this what we see, that f of y plus 1 is irreducible in q of x. Yeah. And so therefore we have if we know that f of y plus 1 is irreducible, so this implies that f of x is irreducible in q of x. Yeah. And this is very obvious, because if f of x is not irreducible, that means f of x can be written as, say, g of x times h of x. Then you just do the change of variable. This implies that f of y plus 1 will be g of y plus 1 times h of y plus 1, which contradicts to the fact that f of y plus 1 is irreducible. Yeah. So therefore, f of y plus 1 is irreducible will automatically imply that fx is irreducible inside q of x. Okay, so I would like to stop here, and we will in the next lecture discuss this similar Eisenstein criterion for polynomial ring in two variable over the complex field. Yeah. So thank you very much. So I will stop. So are there